Okay, make sure you can see my slide, right? Okay. Yeah, thank you for the invitation, and really pleased, to be part of this important symposium. But just like Michael says, it's a pity that we cannot be there in person. So my topic today is what's next after SARS-CoV-2. So it's a very general talk. So I thought I'd do, the usual thing, give you introduction on the bat-borne viruses, because that's my area of research, and touch a little bit of why bats, and then discuss about SARS-CoV-3, and then the VOCs and immune evasion. Michael already gave a very good talk already. And Michael also touched about this spillover versus spillback, how challenging it is for us. And then really extend again from Mike is that I try to address the question, can we develop a vaccine strategy which can help fighting the ongoing SARS-CoV-2 and to be VOC agnostic? But more importantly is now, can we really do something to prevent the next pandemic, SARS-CoV-3? So similarities between fighting virus and the terrorists. And so my really favorite quotes is by former Defense Secretary Donald Rumsfeld. That was made in February 12, 2002. So that was after the 9/11 tragedy. So he classified the terrorists to say it's kind of difficult to fight because you don't know which category. They're the known knowns, and then you have the known unknowns, and you have the unknown unknowns, right? So 9/11 presented as unknown, and before 9/11, when we had the SARS outbreak, which was another unknown. So in this context, virus and the terrorists are very similar, but as Michael says, we should have been able to do better because SARS-CoV-2 is a known unknown, right? So my kind of career, it's really interesting. I was not trained as a virologist or infectious disease, person. I was a biochemist by training. But since 1990, I went to Australia Animal Health Laboratory and I started working on bat-borne viruses. So in the last 25 years, it's almost like my career basically is that I have been dealing with 6 major outbreaks of pandemics caused by bat-borne virus. So start from Hendra and the Nipah virus, and then SARS-1, of course. So this, so Hendra was the unknown, and SARS was the unknown. By the time we get a COVID-19, that's what I think. We should have done better because it's a known unknown. So not only temporarily, right, that's happening, during the last 2 decades, but, sort of geographically, it can really happen anywhere. Hendra was in east coast of Australia. Then we can have, the Nipah virus close to where we are, Southeast Asia. And then the first SARS was southern China, and then we had the MERS, Middle East, Ebola, West Africa, and now COVID back to Asia and China. So that can happen really any place. If you go to PubMed and search for bats and the viruses, before we nail down to say Hendra is a bat-borne virus, before that, so we did that 96. Before 96, very few publications on bat-borne viruses, as a topic. And then by 2020, have almost 1,000 papers per year, and then it's still, 2021 is still going very, very high. So bats and the virus now become a very important topic in the EID field. So are bats special? So I still vividly remember that colloquium, Nipah colloquium in the University of Malaya. That was in 2008. So mark the 10th anniversary of the discovery of the Nipah virus. And one hot topic we debated at the symposium is, are bats special as a viral reservoir? So there are 2 camps. I led the yes camp, based on host genetics and immunology. And then Peter Daszak, who is the CEO of Eco Health Alliance, he led the no camp. He believed that, just because bats lives in high density and have a different ecology, so there's nothing special about bats. So we made a bet at the conference, basically said, let's see, in 10 years' time, see who is right and who is wrong. So in 10 years' time, 2018, Peter published this paper, very high profile paper in Nature, basically says, host and virus traits predict zoonotic spillover from mammals. Among all the mammals, they conclude to say that bats have a significantly higher proportion of zoonotic virus than all other mammalian orders. So I was joking about in my 40 years of career, and this is the first time my competitor published a Nature paper, but I was happier than my own paper because, Science, Kai also published this lengthy commentary, basically interview both of us. So I basically congratulate Peter's group, say it's very important for anyone interested in zoonotic spillover events. And then Dashak, Kai quote said, was gracious in defeat. He says Linfa was right all along, So that was an interesting kind of, 10 years, we had a very heated debate. But now I think most people believe that bats are special, So why they're special, because bats are the only flying mammals and they have this physiological challenge, the stress that we human, mouse, pigs don't need to face, right? Their metabolic rate during flight can be 30 times higher of the resting rate, and their heartbeat can go all the way to 1,000 beats per minute, and their body temperature go all the way to 42 degrees. For any human beings, I say, you will not sustain, you cannot survive this for an hour, not let alone that you have to do that every night for 5 to 8 hours. So that, really forced the bats to evolve. Bats has diverged from land mammal around 65 million years ago. So that's, more than 60 million years of adaptation to flight. This made them to have a very balanced host defense versus tolerance system. So I don't have the time. Today is not, the topic is not about this. But for those of you interested, you can read our, recent review paper in Nature. Basically, we found that bats have this balanced kind of defense and tolerance, much better than humans. On one hand, they have a higher basal level of defense genes like, interferons, Hishel proteins, and autophagy pathways. But more importantly, they have a way to dampen the over-immune reaction like inflammasomes, the STING pathways, and so on. So this has a huge kind of lessons for medical research. It's definitely not limited to infectious disease. So we published another short review, the viewpoint in the Journal of Infectious Medicine. Basically, we said that we can learn lessons in translation from bats to humans beyond just infectious disease. Again, this is not today's focus. So I just put up there if for the audience, if you want, you can read this. So now I kind of put a controversial topic. I know we are still suffering from SARS-CoV-2, and so we should not be really talking about SARS-CoV-3. But for somebody like myself, have been working in this field, I think that's the time to get ready for the next pandemic with a known unknown virus, and we should really do much better than SARS-CoV-2. So I had that idea, I was interviewed by the Straits Times in 2013, less than a year after MERS emerged. For those of you, work with the Thai scientists, I'm a very conservative scientist, but for this area, I'm very, very certain. So they asked me to make a bet. So I said, I'm almost certain that in the next 10 years, a new killer virus spread by bats will emerge. So that was in 2013. As scientists, you're supposed to be happy when you have your prediction, proved to be true. But unfortunately, in our field, that if you got your prediction right, people suffer. And with COVID-19, lots of people die and lots of people suffer. So this is not a fluke, right? We have been prepared for this. This is a grant applied in 2016. Basically, that we say to combat the next SARS or most like emergency by active surveillance. And just 10 months before the COVID-19, I published this review in Current Reviews of Current Opinion in Virology. And in the discussion, basically, so we discuss among the known unknowns, which are most likely be the next one, to spill over the course of pandemic. And we zoom in to bat coronaviruses, right? Okay, so in this context, I think it's not kind of too provocative or too early to think about what's a SARS-CoV-3 will be look like. So this is a family tree of coronaviruses. And unfortunately, we use the same alphabet to name the genus. So we have the alpha, beta, delta, and a gamma. And we know that beta is the most dangerous one because all the emerging zoonotic coronavirus came from that genus. We first had a SARS-CoV-1, then we had a MERS-CoV, and now we have SARS-CoV-2. But there is a subgenus called a sarbecovirus. These are the virus not only that genetically more related, and the most of the species we call it's a SARS-related coronavirus species, but most importantly, these are the virus can use the human ACE2 as a receptor. For some reason, coronaviruses that can use human ACE2 as a receptor can infect humans very successfully and become highly transmissible. Not all of them will be lethal, but some of them can kill. So this is where I think, if you want to predict again, then I say SARS-CoV-3 will most likely be another sarbecovirus. And unfortunately, the hot spot is where we are in Southeast Asia. Okay, neutral antibodies and the immune evasions. So Michael touched a little bit, about our vaccines and, currently just not good enough to prevent variants, and also not good enough to prevent, transmission and the virus shedding. So neutral antibody obviously is an important arm. The other half is the T-cell immunity. People always argue which is more important. I say both are important, but in terms of preventing the virus shedding and the transmission, the neutralizing antibody provide the first line defense. Usually T-cell immunity comes as a later or second kind of line of defense. So I think if we are concerned about immune evasion, then it makes sense to focus on the neutralizing antibodies. Other thing is practically that's the one that you can measure in large scale, whereas the T-cell immunity is still difficult to measure en masse, So many papers published by this Nature Medicine, I think it is kind of a milestone, basically. This is the group led by Miles Davenport from Australia. They demonstrate neutral antibody levels are highly predictive of immune protection. And so this diagram has been shown many times. If you define the convalescent serum from people who recovered from SARS-CoV-2 infection, at least the early days, right? The original ancestral virus from Wuhan. If you define that as one neutral antibody, then for vaccinees, if you receive like the Moderna vaccine, you can go all the way to 4 times high. But if you receive like the inactivated virus vaccine, maybe 4 times lower. So this is around the 10 to 20 times difference in neutral antibody. And you look at the protection of against the symptomatic infections, then there's a very good correlation. Okay. So how do you measure neutralizing antibodies? Traditionally use the live virus neutralization VNT test, right? So you mix your serum to be tested with the virus and put onto a susceptible cell line like Velo. If you have neutral antibody, you block that and then the cell is healthy. If you don't, then the cell will die, called CPE. So it's a gold standard, in terms of specificity and functionality, but has lots of disadvantages, You need a BSS-3, there's a safety issue, takes 3 to 5 days. You need a highly skilled staff and very expensive. So very early on, when I came back from Wuhan, just like Michael, I was in Wuhan in January as well, in 2020. So I came back and I thought, if this virus is going to continue, we need a lot of tests on neutral antibody, especially when the vaccine comes into play. So we developed and published a patent and get a commercial product on a surrogate virus neutralization test. So this is a biochemical simulation, very similar in principle. This is the live virus neutralization test. I already said mix the antibody with the virus, and then you have the susceptible cell with the ACE2 receptor. Using protein engineering, we clone and express the soluble version of the receptor and coat onto ELISA plate. And for the virus, we did not even clone the whole spike. We just zoom in to the most important receptor binding domain and direct conjugate with the HRP. So now a 3 to 5 days of VNT become a 30 to 50 minutes SVNT, surrogate virus neutralization test. So the same principle, you mix the antibody with this IBD HRP conjugate. If you have neutral antibody, you block. If you don't, they bind to the ACE2 codon plate. And so this gives us a very good correlation. So the live virus neutralization here, the SVNT is here, R squared is 0.95 almost. And even better that we can differentiate between binding antibody and inhibiting antibody. So there's 4 monoclonal antibodies in our paper we published. 2 of them have the best binding, but one of them, the red map, failed to neutralize. So that you are doing really functional assay for neutralizing antibody. And also importantly that because you're measuring neutralizing antibody blocking, so you don't have a conjugate which is species specific. So then you get a species independent performance. So in the paper we published in mouse and the rabbit, that was in May 2020. But since then, through our own effort and collaboration, this has been used to many, many different animal species. And I highlight the two, mink and the white-tailed deer, right? So I will touch that later. And everything for COVID has to move fast. I'm joking about it's a COVID speed, So from the concept to developing a test kit, get it published, get patent, get a commercial patent to make a beta test, validate, get a regulatory approval, and officially launch on May 15th in Singapore. All of this happened in 70 days, okay? So I think, I was joking, it's a world record, it's very hard to break. And even more significantly is that in November 2020, so 6 months later, we got approval by FDA to be used as the first test that really approved by FDA to measure neutralizing antibody for SARS-CoV-2. Since then, of course, as Michael says, there's lots of challenges with the emergence of different variants. So as soon as the variants start to emerge, we said, okay, now the challenge is, can you differentiate the neutralizing antibody against different variants? The best way to do that is to have a multiplex assay. So we made a modification. Initially, the receptor ACE2 was on the ELISA plate solid phase. So now we turn this around, put the RBD onto the solid phase, and we use the suspension of magnetic beads from Luminex. The advantage now is because the beads are coated by fluorescent dye. So we can do up to, in theory, we can do up to 100 different sarbecovirus and do that SVNT. So now the receptor binding domain is on the solid phase, and then the fluorescent PE conjugated receptor ACE2 is in the liquid phase. So now you have a multiplex assay. The principle is same, but you're assaying, up to 9,900 different viruses in one go. And also because we quoted the RBD in equimolar concentration on each of the beads, so you actually create that in-tube competition. The neutralizing antibody will, of course, neutralize the homologous virus the best. So you get a very, very high resolution neutralizing comparison. So we use that really to interrogate a lot of studies, including Omicron. So what we found is that Omicron is more capable than expected or predicted from its sequence in its ability to escape the neutralizing antibody-mediated immunity, okay? So we have this as a preprint already posted online. So this is in collaboration with our Thai friends there in the audience. So this is a high resolution multiplex. For the paper, we have a 16 plex, basically 16 sarbecoviruses, all done in one assay, and all we need is 5 microliter of serum, okay? And we assembled 20 different human serum panels, and many of them come from our friends in Thailand. So if you look at the key receptor binding domain, so this is the sequence alignment. So it's a 16 virus we study in this paper. So the top 11 is from the clade2 virus, the SARS-2 related. The bottom 5 shaded region is SARS-1 or clade1. So if you look at the amino acid change, alpha only differ by 1 amino acid residue, delta by 2, beta by 3, and Omicron by 15. So Omicron is here. So then you say, of course, 15, that's a lot of difference. That's why they're so potent in escaping the neutralizing antibodies. But I can tell you that's not the real reason. We have this virus next to it called Reg13. It's very famous. That's the virus discovered in the cave in China and was the closest virus in nature when COVID-19 emerged in December 2019. That virus has 22 amino acid difference. Another virus was discovered in the Guangxi pangolin, we call it P5L. So this is a virus from pangolin. It's also SARS-CoV-2 virus. It has 30 amino acid changes, double even the Omicron. But when you conduct multiplex, neutralization assays, so we do neutralization side by side in the same tube. It's very accurate comparison. Now you look at the neutralization is the best against the ancestral Wuhan, followed by Delta, followed by the bat Reg13 with 22 amino acid change, followed by the pangolin virus with 30 amino acid change, and the Omicron with only 15 amino acid change is the worst among all the SARS-CoV-2 related coronavirus, only higher than SARS-CoV-1, which is, in a different clade. Now, if you look at the job of neutralizing antibody activity, so this is the titer, right? In logs, so on the y-axis, and in the x-axis is the number of amino acid changes. So these are, 1, 2, 3, 4, 5 different, 4 different panels. But regardless which panel, as you can see, you have this solid curve with a shallow slope. These are the viruses evolve naturally without immune selective pressure. That means the virus from bats, from pangolins, from bats, from raccoon dogs. The virus from human, the VOCs, that since the start of pandemic, as you can see, follows a different pattern. The slope is much sharper, okay? So what that says, Omicron is definitely emerged, under immune selection. But it's interesting in Michael's talk, basically, he mentioned there could be advantage because Omicron could be that variant is so fit that in future that maybe no other variant can beat it. We will see, okay? All right, so that's one thing, the Omicron. The other is the spillover versus spillback, right? So, spillover, we call it a forward zoonotic transmission, and a spillback is reverse zoonotic transmission. So animal to human versus human to animal, basically. So SARS-CoV-2, again, posing a challenge that we have never faced before. Traditionally, when studying Hangul, Nipah, SARS-1, we think of wildlife, we only think of it as a natural reservoir or intermediate host or amplified host. But we never really worried about as a spillback host or what we call this, the unnatural natural reservoir. So, but for SARS-CoV-2, what we believe, the current hypothesis, has not been proved yet. We think it's originated from bats, most likely in Asia, and through animal X, pangolin is one of the suspects, followed by massive human-to-human transmission all over the world. Through that process, somehow SARS-CoV-2 is also very easy to pass from human to animals, the spillback. And mink was the first one caught the world's attention and imagination. And mink, because they were developing disease, so these are farmed animals. And then eventually the virus will change, new variants from mink pass back to human. I always say that's really bad, but not the worst, because these are farmed animals. We can contain them, we can vaccinate them, or we can, basically sacrifice them. What we have been worrying, and we had a review paper published more than a year ago, is to say, watch out for wildlife, especially those like in America. In America, we know they don't have the rhinoceros bats, right? So the natural reservoir species does not exist in that continent. But there are other bats in the wildlife. We know they have the ACE2 receptor that SARS-CoV-2 can bind. So if that happens, then you get what I call the unnatural natural reservoir. So this is a natural wildlife, but the introduction of the virus to that population was unnatural by human. And the virus will keep there because usually this animal will not develop disease, right? So become a natural reservoir. Virus will evolve, especially for coronavirus, the recombination that Michael mentioned, and also deletions, point mutations, So then they can transmit to animal X and Y, Z, and then they come back as a new virus. It could be SARS-CoV-3, right? Okay, so that was a hypothetical in 2020. We discussed that. By 2021 or 2022, this is a real, not hypothetical anymore. So for those of you who have been following, I think this is the biggest challenge that, Michael was worried about, this a spillback versus spillover, is that in the white-tailed deer in USA, there are several studies have been conducted using the antibody test. And I was very pleased because they used the CPAS test. So as I said, my test was developed as an animal species independent test. So they use our neutralization test, very specific, measure antibodies from these animals sent to slaughterhouse. And to their surprise, they found that depends on the study and the location, the seroprevalence can go to 40 to 80% of the deer population in USA. Even more concerning is that now you can find every lineage of the human virus in deer, including Omicron already. Okay, and that means the spillback events is not one. It's not one spillback followed by animal-to-animal transmission, multiple spillback. The other is that's exactly what we worried about. You get into wildlife, if that transmission and the infection is asymptomatic, that makes them a truly reservoir-like because you cannot detect the sick animal and you cannot contain them. So that's a huge challenge. Okay, so Michael already said that. So the current vaccines are not good enough. We know that, right? And even as early as last year, John Cohen from Science already argued to say the current vaccine is good, but not good enough. We need to work towards a dream vaccine. A dream vaccine, of course, should prevent shedding and also will be good against future variants. It's a huge challenge, as I will tell you later. So I say that, I have that dream as well, but the dream comes in different generations, just like our mobile phones, right? Our mobile phones, we went from 5G or 1G to 5G, and now we're developing 6G. So coronavirus vaccines are used the same principle, right? 1G COVAX is the one we have got. All the current vaccine is based on the original ancestor strain from Wuhan, whether it's mRNA vaccine, adeno, protein subunit or inactivated vaccine, right? It's all based on the original strain. So already that people say, oh, we need to develop vaccine. When alpha came, beta came, we say we need a beta vaccine. Basically, a second generation vaccine which targeted the variants of concern. Thirdly, then what our group is working to say, can we go even more ambitious to target this whole group, the sarbecovirus, and make a pan-sarbecovirus vaccine? And then there are scientists even more ambitious than us, want to go to the fourth generation, target this whole beta genus, or fifth generation basically is the whole coronavirus family. Okay, so we got really excited data and build up our confidence to say we can make a pan-sarbecovirus vaccine. And that was based on real human data, not just animal data. So that was, from my kind of interest in the SARS patients. So I always interested in the SARS patients because they were infected with the virus. Basically, it's 80% identical to SARS-CoV-2. So I came back from Wuhan in January 2020. Immediately, I went to these survivors in Singapore and asked whether in their serum, they still have neutral antibody against SARS-1 17 years later. And secondly, can they neutralize SARS-CoV-2? The answer is yes and no. They still have the neutral antibody against SARS-CoV-1, but they don't cross-neutralize against SARS-CoV-2. And then a year later in 2021, when they received the vaccine, then I asked the question again. When you receive the vaccine, can this vaccination boost SARS-1 antibodies now? If they can, means there is some cross-boosting, clade boosting happening. And then if that happens, then we have the assay, right? The multiplex assay. We can ask, do they also neutralize the sarbecovirus from animals and other variants? So we think that's going to work is this cross-clade concept, right? The original antigenic thing. If you immunize or infected with the virus and then exposed again, usually your immune system only recognize immunodominant epitope, the neutralizing epitope. So for SARS-1, we use circle. For SARS-2, we use triangle. What we want is this cross-neutralizing epitope, and I put as a cross. So we think by cross-clade this kind of exposure immunization, we may have a hope. And so, the data is published, and the New England Journal actually was kind enough to make an animation. So that's much better than I explained. So I'm going to show the animation now.
SARS-CoV-1 and SARS-CoV-2 belong to the species SARS-related coronavirus and the subgenus Sarbecovirus, but are in two distinct phylogenetic clades. Emerging SARS-CoV-2 variants pose a challenge to the effectiveness of current vaccines. A vaccine capable of controlling current SARS-CoV-2 variants of concern, as well as preventing infection by other Sarbecoviruses, would be optimal. To investigate the possibility of cross-clade boosting of neutralizing antibodies against Sarbecoviruses, investigators obtained serum specimens from 8 long-term survivors of SARS-CoV-1 infection who had received the Pfizer-BioNTech mRNA SARS-CoV-2 vaccine. Surrogate virus neutralization tests were performed to analyze the specimens for neutralizing antibodies against 10 different sarbecoviruses, 7 from the SARS-CoV-2 clade and 3 from the SARS-CoV-1 clade, including variants that affect only animals. The authors examined 5 serum panels consisting of specimens from unvaccinated SARS-CoV-1 infection survivors, unvaccinated patients with SARS-CoV-2 infection, healthy vaccinated persons, vaccinated survivors of SARS-CoV-2 infection, and vaccinated survivors of SARS-CoV-1 infection. All vaccinated survivors of SARS-CoV-1 infection had high levels of neutralizing antibodies against both SARS-CoV-1 and SARS-CoV-2, including several variants of concern. These patients were also the only group with a broad spectrum of neutralizing antibodies against all 10 sarbecoviruses, including bat and pangolin viruses with the potential to cause human infection. In this study, high levels of neutralizing antibodies against a broad range of sarbecoviruses, including both SARS-CoV-1 and SARS-CoV-2, were detected in survivors of SARS-CoV-1 infection who were immunized with a SARS-CoV-2 mRNA vaccine. Further study is required to see whether other combinations of antigenic stimulation from different sarbecoviruses might be able to elicit broad immunity to the entire subgenus. Full study results are available at nejm.org.
Yeah, so this gave us a lot of encouragement to say maybe we can do it, right? But making a pan-something vaccine has been a dream for many, many decades, right? Number one has to be a flu vaccine because the flu is still the most dangerous virus and impact the world, on a much more regular basis than coronavirus. So I was joking about if somebody can get a pan-flu vaccine and demonstrate the utility for mankind, that person deserves 2 Nobel Prizes, Pan-dengue vaccine closer to home, in our region, that's a dream. And now we're talking about pan-coronavirus vaccine, every coronavirus. And I'm trying to work on pan-sarbecovirus vaccine. But in my career, I'm not a vaccinology, but maybe lucky. So the first vaccine I ever developed with collaboration with Chris Broder in USA, it's a hantavirus vaccine against hantavirus that in Australia. And accidentally, we did not do anything special. That vaccine turned out to be genus specific. So it's a pan-hantavirus vaccine. So those of you in the audience working on hantavirus are very familiar now. In the hantavirus genus, we have many bat-borne virus, come from bats to horses to human in Australia, in the Philippines, and then bats to pet, and then to human, Malaysia, Singapore, and the bats human to human, we have Nipah, Bangladesh, and India. All very high case fatality. So my first vaccine really involved to develop is a vaccine against a horse, so that it's a One Health approach. We immunize, and that's a very efficient subunit vaccine, provide steroid immunity. As Michael was saying, the best vaccine should prevent virus shedding. We prevent virus replication, no virus shedding at all. So that basically prevent the transmission to human. Okay, so that was the first licensed vaccine, license that released almost 10 years ago. And it's based on a subunit against the hantavirus, but we demonstrate the same vaccine was 100% effective in prevent lethal Nipah virus challenges in different animal models. So now CEPI has funded this project. We are going to convert this Hanja soluble G vaccine into a human Nipah virus vaccine. So this is the first example of a pan-genus vaccine can be done. All right. So, are we ready for SARS-3? This is the challenge, right? So Michael, again, beautifully demonstrated that to succeed, we need a science and technology. I think a science and technology are largely ready. What we are not ready is the geopolitics and the legal framework. When you have an outbreak in a country at the earliest stage, we don't have a legal framework and have the system to work together, use the best knowledge, the best talent in the world, and to solve the problem together. So that's something I think we really need to work better. In terms of preventing the next, pandemic, what can you do, right? I always think, I have been in this game for 40 years now. There's 3 areas you can do. Number one is the most ideal. If you do enough pre-spillover surveillance and mitigation, animal-human sort of interface transmission, if you can prevent at that stage, that of course is the best, right? But as the pandemic proved again, even for H5N1, we have a huge international surveillance network. We still could not predict and prevent. So the next best thing is to have early warning and detection system, and that especially in the hospitals, ICU units, if you have unusual. And the doctors in Wuhan did a good job. They already sent sample for next generation sequencing in middle December. But I think the response, the systematic response was not good enough. Individual effort was there. And then the last result of us countermeasure, as Marco says, we were so successful, from the pathogen sequence to a vaccine in 10 months, basically 200 days. And yet we are still in the thick, middle of the pandemic. So that's what I say. Countermeasures are great to have, but it's the last resort. If we can do at 1 or 2, it will be better. So in that context, I'm very pleased and proud. In Singapore, the government is very, very proactive. They just, put $130 million research program for a research in epidemic preparedness response, and called PREPARE, the acronym. And I have the privilege to be really appointed as the founding director, executive director, lead that program. So there are 5 research pillars we're going to do, real-time data analysis, modeling, and environmental transmission, diagnostics, countermeasures, and last but not least, regional networks. So that allows me to work with you guys in Sri Lanka, in Thailand, and in other countries in ASEAN much more closely. To underpinning this, we have 2 long-term core capabilities. One is the clinical research database, and the other is the biobanking, biorepository. So that it's very important in the early stage of response to outbreak. Even for your assay validation, you want something already in your biobank you can use, either as positive control or negative control. So the overarching objectives is going to focus on capabilities, platforms, and expertise. And then very important at the national level, interdisciplinary, and peacetime, really that we have to do all of this, and also rapid deployment. Really, this is not research for research sake. This is a research for impact on the ground. And it's a very high level, so I'm the executive director, and David La, a clinician, is my deputy. And below this, we have the leaders for the 5 pillars plus 2 cores. But importantly, it's a research program for the first time is parked within the Ministry of Health. And I report directly to a steering committee chaired by the director of medical sciences and the chief health scientist, So, and it goes all the way to the government. So, and with that, I'd like to thank my team. The last time we were allowed to have a party was Christmas 2019, without realizing that, 1 month later, has to be working 14 hours a day, no weekend, no holidays, basically. And lots of collaborators, in Singapore and also internationally. And then the TRC EID is, of course, a very strong collaboration. We have been working very, very closely. And I thank for all my Thai colleagues, And just to do a little bit of a plug-in, that I'm chairing 2 quite important conferences to come. One is April 10 to 13th. It's not too late for you to at least register for the online. It's a hybrid version. So this is the Keystone Symposium on EID and the lessons from the pandemic. And then November this year, that the 7th World One Health Congress will be in Singapore. And I'm sure many of them in the audience will come. Thank you for that.